bypass that particular part. With that, I would love to thank board organizers and the panels to help with support with this competition, and we really are really grateful for this opportunity. And also, would like to thank the funding agency who support this research. And I would like to answer any questions. Thank you.
Thank you, Boyon. That was amazing. Do we have any questions? This is the only mic I have, so I'm gonna pass it around.
Yes, thank you for
Thank
your talks. So can I understand that there's like no RL from like there's no system for RL for human feedback or something, and we you are not fine tuning the language model itself, right?
That's right.
So can I ask do you think that is there any possibility to like fine tuning the language models to so that the like the prompts that so that the model like returns like more kind of more appropriate models that follows our prompts, and do you think that such kind of fine tuning fine tuning can improve the results? Do you have an
Yeah.
idea?
Yeah, this is a great question. So, in fact, this is the very next step we're working on. So, you're right on the spot. We're actually working on things that, right now we're basically delivering these models as sort of fast ideation at the beginning step. But we actually think if you can complete the loop, right? So you can deploy the robot in the real world and you can observe the behavior of the robot in the real world because that's eventually, in the end of the day, we actually want to deploy these robots, so we can get the outcome of the results and then generates the feedback. Either we can fine tune the initial foundation model to generate better meshes and better robot design, or we can actually add more intermediate step of models that take in the feedback across different steps. For example, is this robot manufacturable? How much cost we actually spend on manufacture this robot? How much time that we take on that? And also consider all of these factors as inner loop, optimization during this process. So I think it's definitely possible. There is a lot of space to improve, especially, we pick the quadruped robot as an example because we saw this is still a very challenging task for human students, experts, take several weeks and months to accomplish this. But the next steps we want to do is actually to be able to generate a robot, even the completely new electromechanical system design, by taking into more sort of the feedback loop on top of that.
Yeah, sounds cool. Thank you.
Thank you.
Okay. I'm being told we're out of time for more questions. So
Feel free to reach
uh,
out.
yeah, yeah. Thank you so much, Boyuan.
Thank you. Thanks, everyone.
So next up, we have the third place overall winner. Um, and we have Alexander here to give this. Okay. Are you in Zoom? Okay. We'll have you present. Yeah, share by sharing your screen. Yeah.
Also make a plug-in HDMI. Yeah. Yeah. On the other side. Okay. And, oops. Yeah, I'll use audio also. And do I need to enable mic on Zoom? It's actually enabled here. Okay. Okay.
Oh, the audio is coming from HDMI, so I guess it's coming from here into the. So mute this one.
Well, I also have some audio in slides, but
Yeah, so
let's see.
it's coming.
I'm sorry. I'm.
And you need to share the screen as well.
Oh,
Sorry, I thought you.
I'm sorry. Yes. Does it work?
Yes.
Oops. Oh, sorry. Wrong button. Yeah. Okay, so I'll show the slides again for remote viewers. So there was a video of two creatures from different worlds struggling to survive in a world with different parameters. And this is the example of violation of mass conservation. So here, glider died in rotator world, and then rotator will die in a glider world. Okay, moving on to the next slide. So yeah, particles create fields, and then each particle greedily follows the local gradient of the fields they create. And field has two components in it. One is repulsive component, which is just like accumulative. It's like superposition. And the second component is a little bit more involved. So each particle creates like a ring around it. So together they create a kind of landscape. But then there is function G that selects particular elevation level in this landscape, and all particles want to be in this green area where they're happy. So this is inspired by once again by original linear formulation by Bertrand. And then what's nice is that we can look at total energy of the particles, and it's has well, first of all, total energy decreases non-monotonically because particle greedily follow the gradient without taking into account how their displacement will affect the energy of other particles. And also, when I try to add audio, let's see if it works. So here, the frequency emitted by each particle is dependent on its energy. Yeah, that's how when I was making a video, I wanted some sound, and these energies came out very nicely to Sonify. And also these okay, maybe like this. Oh, yeah, but Well, anyway, I'm not sure we'll do it. Okay, how do I have it?
It should be sharing because you're doing the HDMI.
Yeah, but okay, video, audio is not the main part, of course. It's,
Yeah.
and I tried to put mic closer. Did it work? Okay. So there will be another piece where I'll show audio. Okay, and also these energies, these energies are useful for like analysis of different runs because it gives you a single number by which you can cluster the outcomes of the simulation. So here the same rules, different random initial placement of points, and there are like a few different attractor states of the system with various like final energy level, and sometimes system like somehow stays on the same energy level. Sometimes it jumps. Sometimes it can even rise a little bit in its energy. And then, well, it's also natural to try what would happen if we optimize global energy instead of local. And as expected, we get convergent behavior. So here, this video runs global energy minimization for first 2,000 steps, and then switches to local energy optimization, so which leads to rise in total energy and this dynamic behavior. Then we also demonstrated that, well, a nice property of PDEs that they are kind of can be kind of resolution independent in theory, that you can change the resolution of the grid you're running on. And here you can achieve kind of similar effect with increasing number of particles and also scaling the radiuses of these individual particle fields. So here I get the same very similar attractor by that has 4 times more particles. Then I have this video which I'll accelerate so that it takes 2 minutes, which shows oops, I'm sorry, a few different, a few examples of creatures that exist in this world. Okay, accelerated. It will take 2 minutes. The budget. This is the energy landscape. This is correct. This is the demo that we published. And those, so it can be used to, you can capture creature as a PNG file, and this PNG file encodes the positions of particles, so actually it can be shared on media, and then one can drop image posted, say, on Twitter onto the demo, and it's supposed to come to life. But unfortunately, we've never seen anyone using this feature. Also, particle Lenia happened to be the very first simulation that I implemented when started working on SwissGL. So it was like case study that I made Swiss jail so that I could implement particle linear. Sorry, it's too early for this slide. And I want to, there is a well hidden feature in this demo. There is toggle audio. So it has a bit different audio style. I wanted it to sound like a swamp. Okay, and then also some time ago I released the tutorial that on observable platform that shows how to implement particle linear with pure JavaScript from scratch without relying on automated differentiation, because original implementation was using JAX, and here I just write derivatives manually, show how to write this code. And once I posted it on Twitter, then this person, I'm not sure how to pronounce their name, but came up with this amazing video where he visualizes the energy level with emojis, and they're so cute. Okay, thank you. Questions, please.